In this video, we're going to look at atom economy. In the last video, we looked at percentage yield. Percentage yield is important because it tells us about the efficiency of a reaction, or indeed the separation and purification. It tells us how much of our starting material we're likely to actually turn into the products. But atom economy tells us a little bit more. It tells us about the relationship between the useful product that we actually want and unwanted waste products. For example, the water that's produced as part of the neutralization when I'm trying to make a salt. So if we want to manufacture a particular chemical, yield is important, but it's not the only thing that we need to consider. If we look at this method of extracting titanium from titanium chloride, then we heat it with magnesium. The titanium is the desired product, but we're also making magnesium chloride. And when we're manufacturing chemicals on a large scale, something like this can be a bit of an issue. So atom economy, like yield, is another calculation, and it's another one that is calculated as a percentage. So you need to make sure you get them clear in your mind and don't confuse them. It's calculated like this. The mass of the useful product, so in this case, in the previous example, titanium, divided by the total mass of all the products you make, and then times by 100 to make it a percentage. So it tells us about the proportion of useful things obtained compared to the reactants used. Let's use the titanium example to do this atom economy calculation. Titanium is the useful product and it has a relative atomic mass of 47.9. We're just making 1 mole of titanium in this reaction. The RFM of magnesium chloride is 95.3, but we're making 2 moles of it. So that means the total mass of the products will be 47.9 plus 95.3 times 2. So don't forget to actually include the useful product in that part of the calculation. So it would look something like this, 47.9 at the top, that's my titanium, over total mass of everything underneath. And we can see that the atom economy of this reaction is therefore just 20.1%. So almost 80% of the mass of the chemicals that are going into this particular plant are being transferred to waste products. And this is important for 2 major reasons. Firstly, we have to transport the chemicals, the titanium chloride and the magnesium, to the plant. That's going to cost money, and it costs energy, which probably involves using fossil fuels. And the heavier they are, the more money and the more energy that is going to take. And then second, we need to dispose of the waste products. We can't just sort of leave them lying around. So that could be expensive, but it's also less sustainable because we could be wasting valuable materials. So how can we improve atom economy? We need to reduce the mass of wasted products just in comparison to the mass of the useful products. And there are 3 main ways we can do this depending on the type of reaction, what we're trying to make. The first one is we could just choose a reaction with a single product. So the Haber process, for example, which we've come across before, making ammonia, this is 100% atom economy because ammonia is the only product, and therefore the mass of the useful product is the same as the total mass of products. But that's not an option for a lot of reactions. So what else could we do? Because with a lot of reactions you just can't make what you want as a single product. Another option is we could change one of the elements in the starting materials and thus in the waste products for one with a lighter relative atomic mass. So let's use this example here. We're using 2-bromopropane, don't worry too much about that wording right now, and sodium hydroxide, and we're making propan-2-ol, which is our desired product, and the waste product is sodium bromide. So the atom economy of that is only 37%, and it's because of the mass of the sodium bromide related to my propan-2-ol, which is what I'm trying to make. I can't change the mass of the thing I'm trying to make because obviously the thing I'm trying to make is a fixed thing. So there are two things we could do. We could choose to use lithium hydroxide instead of sodium hydroxide. That would improve it to 41%. Or we could use chlorine in our organic molecule instead of bromine, and that would improve atom economy to 51%, because instead of producing sodium bromide, producing sodium chloride, and chlorine is a lighter atom. However, that might not actually be feasible because it can change the relative reactivities of starting materials, cause problems, it could make the reaction too slow, or it might just be that some materials are rarer and thus more expensive. So for example, lithium hydroxide is probably a lot harder to get hold of than sodium hydroxide, so it might not really be viable. So the third option, which is available with any reaction if we get a bit creative, is to find a use for the other product. Perhaps a use within the plant, so many chemical manufacturing plants make more than one substance, they don't just make one thing. Or you could sell it to another plant or another business that has a use for your chemical. This then avoids your disposal costs as well. But of course, atom economy isn't the only consideration to take into account. If we went back to our ammonia example, then it's 100% atom economy, which is great, but it has a really low yield because it's a reversible reaction, and it's very difficult to get conditions that get the yield really much higher than about 15%. We could change the conditions, such as lowering the temperature, but if we do that, you may remember from studying this before that increasing the yield then gives you a slower reaction rate, which then makes it really not feasible. So atom economy is not everything. If we look at two methods of producing ethanol, we can look at other factors that we might want to consider as well as yield and atom economy. So reaction 1 is one way of making ethanol using the hydration of ethene, catalyst, high pressure and temperature. It has 100% atom economy because it's an addition reactant. I'm adding two things together, there's only one product. It's got a high yield of 95%, so it's not really an equilibrium reaction. It more or less goes to completion. It's easy to get your product separate because there's only one product. Meanwhile, if we looked at the second reaction, which is fermentation of glucose using yeast, then the atom economy for that is only 51.1% because we're losing that CO2, and the yield is 15%, not because it's not about it being reversible reaction, but any higher alcohol content than that will kill the yeast, so you can't really get them to produce any more than that in solution. But these aren't the only things, because if we just looked at those numbers, we'd think that hydration of ethene would be definitely the best way to make ethanol. But when we consider the conditions, hydration of ethene involves high temperature and pressure. That's going to be expensive in terms of use of fossil fuels, most likely to provide the high temperatures, expensive equipment to maintain high pressure, and of course it's not overly sustainable because of the use of the energy costs. Whereas also the other problem is the raw materials that we're using. So we're using ethene is most likely to come from cracking of crude oil, which is not as sustainable as glucose, which we can get from plants, and that's renewable. Whereas the other thing about reaction 2 is that it takes place at room temperature and pressure, which also makes it in many ways much more sustainable and a cheaper way of making ethanol, despite the low atom economy and percentage yield. So if you want some more help with your A-level chemistry calculations, I've got a full online course, which actually this video was modified from. It's called Confidence in Chemistry Calculations. And at the moment, you can get that absolutely free for 2 weeks. Let me just show you what's in the course. So there are 8 different modules which look at the essentials, equation skills, relative atomic mass, formula mass, empirical molecular mass, percentage yield, atom economy, all these different things, titrations, loads of stuff on solutions, calculations, also Avogadro, and long answer problems. So there are some like really more challenging ones, and it comes with a full booklet of different chemistry calculations with full mark schemes and explanations as well. All of the more difficult questions that I put on there have video walkthroughs. So you don't just get a mark scheme, you actually get how to do it. Each one of these modules has like at least 6 different lessons in it, quizzes and ways to assess yourself. And actually you can access this course as part of my A-level revision memberships, which includes loads of other different topic videos and practice questions, and not just the calculations course. So the calculations course is included in the bronze, silver and gold membership. The only difference between the 3 of these is that with the silver membership, you get a full monthly assessment where you do an assessment exercise and I mark it for you, give you that examiner's perspective, give you personalized recorded feedback. And with the gold membership, there's just a few spaces left for my AQA and OCRA group chemistry lessons. Those are for year 13 because my year 12 course is full. But if you just wanted to try out the bronze membership, which is only £5 a month anyway, including the whole calculations course and 22 other different topics, along with practice questions and masterclass videos, that's actually available right now for a 2-week free trial. So you can try it, see how you get on, and if you can't even afford the £5 a month, you could sign up if you've got like a mock exam or a retake coming up. So go to my website, ckchemistry.co.uk. You'll also find loads of free revision downloads there as well. And of course, subscribe to my YouTube channel because I'm going to do at least 1 video a week and probably 2 for the next term or so.